Hello and welcome to a final laboratory report about the drag coefficient and dynamic drag force response of different lengths. We are students in ME 30801 Fluid Mechanics Lab, and this is our open lab project. We are Division 2, Team 24. I am Dean Smith, and my partners are Jack Bennell, Carlos Morales, and Dominic Hollifield, all in the School of Mechanical Engineering at Purdue University. There are many occurrences of flags and other soft-bodied objects that blow in the wind. This flapping motion often results in larger drag forces when compared to a static body, but can be difficult to determine while purely using theory. The purpose of this lab is to explore how the drag that a flag experiences changes with respect to the length of the flag and the wind speed. The results of this lab could be used to control vibrations of a flag to reduce wear on the flag or to ensure the flag doesn't damage the object that it is attached to. Also, using these results could help account for the cyclic loading effects of a flag-like object that would induce fatigue failure. The first goal for this project is to find the period, amplitude, and average value of the drag force of a flag-like object and how these properties change with respect to flag length and wind velocity. The second goal is to find the drag coefficient of a flag-like object and how this changes with respect to flag length and wind velocity. The third goal is to find how the oscillating drag properties compare with the non-oscillating drag properties. All goals must be measured by Tuesday, April 18th, and all data must be analyzed, reported, and presented by Friday, April 21st.
The facility and instruments used in the lab include the wind tunnel, dynamometer, and data acquisition system. The wind tunnel, which can be seen in the image on the right, has a test section with a length of 2 feet and a width and height of 1 foot. It has a wind speed range of 3 to 38.7 meters per second. The dynamometer, which can also be seen in the image on the right, is a device that converts the force and drag acting on it to a voltage output. The voltage output is measured by the data acquisition system and can be later converted back into force measurements. The test model for this lab was created by attaching a flag to a 3D printed flag holder which was fixed to a threaded rod, with the rod then threaded through the dynamometer stand. The flag was made from the Waverly purple fabric that can be seen in the top left image. The flag had a height of 13.5 centimeters and a length ranging from 25 to 7.5 centimeters. The flag holder, as seen in the top right image, was modeled in CAD and then 3D printed. The flag was then fixed to the 3D printed part using double-sided tape. Then the flag and mount were able to be attached to the rod and threaded into the dynamometer. To conduct the experiment, we first started with a flag of length 25 millimeters and measured the drag force using the dynamometer and LabVIEW program. This was done at 5 different wind speeds, which can be seen by the variable frequency drive inputs on the left table. At each speed, slow motion video is captured in order to identify the period of oscillation. This is found by counting the frames between a full period of the flag and then dividing by the frame rate of the camera. The frame counting process can be seen in the video on the right. The process of measuring the drag and period at each speed was repeated for each length value that is seen in the table on the right.
The data we collected for this experiment included the VFD frequency of the wind tunnel, the dynamometer sensor readings, and videos of each flag at different wind tunnel frequencies. We converted the wind tunnel frequency into wind speeds in meters per second using a best fit curve created from the wind tunnel introduction manual. We used the wind speeds as a dependent variable for our analysis. We then converted the dynamometer voltage readings into drag force using the drag force equation. K is the calibration constant, V total is the voltage reading at the specific data point, V naught offset total is the reading with the model stationary, VTS is the reading of the model without the flag at the test speed, and V naught offset TS is the reading of the model without the flag and stationary. final equation needed is to find the oscillation frequency of the flag. The video was recorded at 960 frames per second, so to find the frequency, we simply divide the frames per second by the number of frames.
The first aspect that the team wanted to observe from the test was how the effective drag coefficients of the flags would compare to the skin friction drag of a flat plate of equal size. In our proposal, we predicted that due to the kinematics of the deforming flags, the drag coefficients would be significantly higher compared to that of a flat plate. From our results, we found that this prediction was true, and in figure 4.3, we see that the flags had a drag coefficient that ranged anywhere from 0.3 to 1.6, compared to those of the theoretical flat plate, which we calculated to be 0.07. Another prediction we made in the proposal was that increasing the flag length would increase the drag force due to the larger forces caused by the larger deformations of the flag. We found that at higher speeds the prediction holds true, however for lower wind speeds this relationship becomes less clear. We finally wanted to observe the dynamic response of the flags by looking at the amplitude and the frequency of the measured force. In figure 4.4, we see that the frequency of the flapping increased with an increase in velocity, but also increased as the flag length was shortened. This is a phenomenon that we were curious to find for this experiment since we had no idea how the flag length would affect the frequency. Another interesting aspect we found about the dynamic response of the flag was that for our shortest flag, there was a speed at which the flag began to flap. The other flag's flapping was induced almost instantly. However, for the shortest flag of 0.07 meters, we found that it would only start flapping once it reached a speed of about 10 meters per second. This is a phenomenon that we were not expecting to find in our lab and would be interested to perform further testing on. There are two main limitations to this lab setup. The first limitation is that the dynamometer did not have a fast enough refresh rate to be able to measure the sinusoidal loading directly. Instead, the frequency needed to be measured separately by using slow motion video of the flag to determine the frequency at which it oscillates. This process made finding the dynamic response of the flag more time consuming. The second limitation is the possible added kinematic effects of the dynamometer and the flag mount. We noticed that during testing, the dynamometer and the flag mount were significantly vibrating during testing, which may contribute their own kinematic effects on the measured drag force. Overall, we were able to show the increase in drag force and effective drag coefficient for a flag versus a plate. We were also able to show the positive correlation between the increase in length of a flag and the increase in drag force. However, our results for this relationship with the drag coefficient may be inconclusive due to the small number of available data points at higher speeds, due to the flag being damaged at these speeds. We were also able to characterize the frequency response of the flag for each velocity and the flag length and showed a clear positive correlation between the frequency and the lengths. Two suggestions we would have for future work would be to shorten the flag mount in order to reduce the kinematic effects and to increase the sampling rate of the dynamometer.